Yes, so thank you for the introduction. I'm giving this talk on behalf of Daniel Fenner, who did most of the work together with all my wonderful co-authors listed here. And I'd like to start here with a very simple depiction of the urban boundary layer, which is actually shown on our logo that was designed by John Arnfield and Tim Oak a long time ago. But the logo is really nice because it shows us the influence of cities on the atmosphere, and in red, of course, the urban boundary layer. Of course, one has to think that there's wind coming from one side and creating this urban plume, modifying the atmosphere. And you see here also the mixed layer height indicated. This is one of the parameters we are looking at. And as a hypothesis, one can argue if the city is heating more the atmosphere, the mixed layer will be deeper. It might also cause additional cloud, boundary layer cloud, as seen on the logo. This work I'm presenting is part of an ERC grant called Urbisphere, Coupling Dynamic Cities and Climate. And I'm presenting here an observational campaign that was run in the city of Berlin in Germany for a full year from October 21 to September 22. And why do we need observations at that point? We have wonderful models, as we've seen, but those models also need to be supported in terms of providing data for model evaluation, but in particular also to see whether the physical understanding of the processes that modify the atmosphere are properly represented. And for that, we have used a whole set of boundary layer observations, mostly based on automatic Lidars and ceilometers, so lasers that shoot up in the atmosphere and get backscattered from the aerosol in the atmosphere, but also microwave profilers, Doppler wind Lidars, and radio soundings. And one of the special aspects of this campaign was not only looking up in the atmosphere, but concurrently looking at the surface and the fluxes at the surface, how those fluxes might differ between the surrounding and the atmosphere. So I first would like to go over how we have planned that experiment. You see here a map of the Berlin greater region. In gray is the built-up area of Berlin, and we have here defined two rings, an inner ring, which is the dense city center in blue, about 5 kilometers, and then an outer ring, about 20 kilometers, that contains most of the built-up area. But the influence of the city on the boundary layer might go well beyond that. We have here also a typical wind rose, long-term wind rose, and you see the predominant winds come from west, but we also have easterly components of the west-east axis, and that was one of the reasons to essentially sorry, that was now too fast, to set up a line of instruments. So all those dots that are in black are ceilometers in a line with the wind, so we can follow how the boundary layer is modified as air flows across the city. And secondly, for looking at the lateral transect, or less often wind directions, also having a perpendicular transect. One of the interest as well is looking whether the boundary layer is the same all over the city, or if different areas of different density have actually an imprint on the boundary layer height and other mixed layer height and other parameters. So there's an intra-urban grid here with additional instruments in a very dense part of the city. And this was the experimental setup from our side and from partners. And that's complemented with the operational network. So the blue dots are other sites that are in the region that give us also some idea about the background situation. I will now look into a couple of cases to figure out whether we can see urban effects. We start with because I said we look at seasonal differences in a winter situation, a winter day, relatively cold, with a shallow morning mixed layer. And fog was observed across the region, but also some boundary layer clouds developed during the day. The wind was in this case from the south. And you see the surface energy balance graph to the right-hand side, where in orange we have the urban fluxes and in green the rural fluxes. And I will reuse this color coding throughout the presentation. And you see already that the sensible heat flux is significantly higher in the city compared to the rural area, while there is relatively little evapotranspiration or latent heat flux available. If we now look at how the mixed layer developed over the course of that day, you see here a typical backscatter profile, so time on the horizontal axis, height up to 1,500 meters on the vertical axis, and the color gives us the aerosol not directly the aerosol content, but the backscatter, which is proportional to the amount of aerosols sending the laser back. And you see in the morning where it's labeled, there is a fog period. In fact, fog was observed at nearly all the sites except for the inner city. That was an interesting feature that we can actually see low-level clouds. And then what's also seen in the midday is that there are some red pixels around over 1,000 meters. Those are boundary layer clouds that develop. Then the black dots, that's showing the methodology, are the derived mixed layer height values based on Simone's algorithm using StratFinder. And you see the mixed layer is relatively shallow, about 200 meters throughout the night, and goes then up, rapidly growing and decaying. The end. If we compare the different sites, you see that on the right-hand side, there is not much difference during the daytime. So they all show roughly the same height, but in the night, in the early morning, we have larger differences. So let's go to a time of the year where we expect stronger forcing. For example, going to spring, it's good because leaves are not fully emerged, so the city warms up quite significantly, but there's not a lot of transpiration, and there's big differences between the surrounding and the city. So this is a spring day with wind from the northeast flowing towards Berlin, and it's a nearly cloud-free day. There are some cloud, interestingly, over the city, not over the upwind area. And you see, again, the surface energy balance graph shows us large difference. The bond ratio, for example, at the rural side is around 1, but at the urban side, we have 5 times higher fluxes of sensible heat compared to latent heat. So there must be strong differences now in the forcing, much higher values. And we separate now the sites into upwind sites, city sites, and downwind sites to look at this. And if we, again, employ StratFinder on all those cases, we haven't labeled the individual sites, but the colors tell us where the sites are. So the yellow sites are sites upwind, and you see as we move across the day, those are the ones that are the lowest. They are at about 1,500 meters, where the sites in the city indicate the mixed layer is now moving a couple of 100 meters higher. And the interesting thing is the downwind sites, they stay at that high level. So we really have the picture from John Arnfield and Tim Ogg in this case, where the urban plume is elevating the flow. We were wondering whether we can also resolve that in model. So this is now a model product of the boundary layer height in the afternoon. And the color coding tells us the height of the boundary layer height in the UN model with 300 meter resolution, urban parameterizations in there. And the rings are the different sites, and the color inside the rings is the height that was measured. And the measured height actually quite nicely matches the value from the model. So we can compare the values of averaging just the sites that are upwind in yellow, city in purple, and downwind in blue. And you see upwind sites with 1,500 meters, city sites at 1,830, downwind sites 1,900 meters. And even though the model is not perfectly reflecting those heights, it has the same order. And interestingly, we also see that the growth rate of the mixed layer in the morning from 9 to 12 is strongest over the city. That's also an indication that there is more energy put in from below into this. Now, this is an urban plume case we can also demonstrate from other means. For example, satellites that they here, tropospheric NO2 column, you see the same rings with 5 and 20 kilometers. So we can spot where Berlin is, winds from the northeast, and you see an enhancement that goes nearly 100 kilometers downwind, a clear plume. And interestingly, also as it goes on during the night, here ground weather stations show that we have a differential warming across the city. The northeast is cooler, the southwest that is affected by the urban plume is warmer. Now the last case, that's what we are often very interested in, are heat waves. This is a heat wave case, one of the second hottest day of the year, 37 degrees. And during that day, we not only had the network of Lidars running, but also concurrent radio soundings upwind and in the rural sector. And one of the things I wanted to point out, you can also put those instruments on vans. So here is our van with the laser built in, and you can drive to any location and be flexible in terms of wind. So if the wind comes from the south, we could add a station to the south and have an upwind station, which was pretty cool. You can actually also do transects. So looking at that day, you again see very strong forcing from the radiation, but interestingly, the fluxes are pretty much the same over the rural and the urban area. So this was a relatively dry period, and the sensible heat fluxes are not that much different between city and surrounding. And not surprisingly, then the mixed layer height derived from the StratFinder algorithm shows more or less the same, no statistically significant difference between the city and the surrounding. So it's not a universal picture what we have on our logo. It is depending on the context, on the weather situations. Nevertheless, there are differences, of course, and we all know that heat waves have also or cause strong differences with the urban heat island at night, and we can actually contribute to the three-dimensional picture. Here are radio soundings done concurrently outside the city and in the city. So the dotted lines are the rural, the straight lines the urban ones. And although in the higher atmosphere they look relatively the same, there are differences in the morning where the urban growth is faster, and in particular in the late evening where we have a significantly warmer atmosphere across the entire boundary layer still over the city. To illustrate this, here again, the massive heat island magnitude, or the range from 23 to 33 degrees in the evening of that day, that now shows that in the nighttime we have quite different forcing compared to the mixed layer during the day. So let me summarize this. We didn't do a fully comprehensive analysis. That's still up to be completed, but we look at seasonal and diurnal differences. So in winter, we have a shallow morning mixed layer that was higher. We had less fog in the city observed, and then rapid growth after the fog dissipates, of course. In the spring, we saw the biggest differences, over 10% increase in the height of the mixed layer, pronounced differences. And the interesting thing was upwind, lower height over the city. It was elevated, but it stayed elevated downwind. And in the summer heatwave case, no systematic differences. The mixed layer height was found during the day. The energy bands had little differences. And in the evening, of course, the corresponding difference. So I'd like to, again, thank the co-authors and the team for making those massive observations possible. And I'm sure we will be back as well in the next conference with more detailed and comprehensive analysis. Thank you.
We have time for, yes, question, please.
Hi, Andreas. Thank you for the nice talk. I was just wondering what were the other components that were retained for the placement of the different stations that you have set up in Berlin. So you had the wind direction, that was the main objective, fair enough. What were the others?
So we have a perpendicular one, so we have a long wind, perpendicular, and then an intra-urban grid. So the perpendicular one, if the wind is along the transect, should presumably also give us a elevated mixed layer over the city as opposed to the side, where it's not influenced. So we can actually have a two-dimensional cross-section. That was the main purpose, but also one can argue wind is not always, we cannot control the weather. So if wind is from north, we can also analyze upwind, downwind. That was one. The intra-urban grid has the main goal of looking at, we model Berlin with 1,300 meter and 100 meter resolution. And with increased model resolution, we also create more differences or variance in the mixed layer height to see whether that's actually also fine in the measurements and see whether larger parks actually can have an influence, or is that not relevant? Yes.
Okay. Yeah. One else.
Andreas, great presentation. You showed those energy bands, right? There was
Yes.
always more Q star in the urban area.
Correct. Yeah.
But then there was a pretty big difference in bond ratio, almost 1:5. But then when you look at the heat wave situation, interestingly, they were pretty similar in bone ratio, but you still had a pretty big Q star difference. What do you think each of this?
So that the Q star is low, is higher over the city is expected because of the albedo effects and the shading and trapping. Yes. The bone ratio is still the same. It's controlled by the water availability, and that summer period was very dry, and soil moisture was limited. So I guess it was more a limitation, but it could still mean that there was a little bit more evaporation that just made it to happen from the sensible heat flux the same. So that's good.
And what percentage of Berlin is like vegetated? If you have to say.
It's quite a vegetated city. I mean, percentage depends on the neighborhood. Hard to say, but there are big parks in there as well, yeah, and forests that are part of the city. Yeah.
Time for a 30-second question from Jason.
Yes, did you do a fall measurement? And the second is, what's your explanation of initial thoughts about the summer? Why is there not such a gradient of time?
Yes, we did, of course, also fall measurements. So the array would run continuously for a full year, actually even a little bit more. So we have all those sites for a full year, and that's yet to be explored. Why it's not different in the summer? I mean, we also have seen that from the presentation of Simone from Paris, that the heat wave situations seem not to cause significant difference in mixed layer height. Whether that's a universal finding, I would not say at that point, but given the energy balance, it's clear that if the sensible heat flux is roughly the same at both sites.
It's very high.
It is, yeah. It's 3,000 meters, but that surprised us as well, but that's the case in a continental climate, yeah.
So lots of excitement over your talk, and I invite everybody to please swarm in after this session. So let's thank our speaker once again. So we started the session at National